and even another. So in today's topic, we're going to look at the atomic structure. The atomic structure. That's what we're going to look at today. Structure. So we have to start with what is an atom? What is an atom? So an atom we can describe it as the smallest particle into which elements can be divided without losing their chemical nature. That's what we call an atom. The smallest particle into which chemical elements, if an element will be divided, can be splitted or divided without losing its chemical nature. So, history of an atom. So, in the 1800s, John Dalton suggested that all matter was made up of tiny spheres that were able to bounce around with perfect elasticity and called them atoms. So John Dalton was the first one to identify an atom in the 1800s. He knew they bounced elastically. So what he did was he saw there were tiny what spheres and they were able to bounce elastically. Hence he called them atoms. So John Dalton was a chemist, by the way. Chemist. He was only brought up this idea of atoms. Atoms are invisible and indestructible particles. You can't destroy nothing. Not the smallest parts of in. So compounds are formed, two or more atoms are combined. That's when you form what? Compounds. It's two atoms. You have atom A, you have atom A and atom plus atom E in the drawing. When it gives us compound. Let's give us a compound A, E, E. Yeah, give us a compound A, B. So a compound are formed from two or more atoms mixed together. So John Dalton was the first one to see that suggest that matter was made up. So let's not forget matter. This word. I said matter. This word matter was made up of tiny spheres that were able to bounce around in perfect elasticity. That's what it is. So this is where a theory of atom comes from. So this is mostly brief history. So in the late 1800s came a English scientist by the name of Joseph John Thomson. Thomson provided the first hint that atoms are made of even smaller particles. Okay, so J.J. Thomson provide, provided the first hint that articles were even smaller as delta dots. Yeah, they were even smaller. So he proposed also the Coulomb Putting models. So atoms were made of, made from a positively charged substance with a negatively charged electrons scatter about like raisins in a pudding. A pudding language you can say chocolate. So when two atoms put together and scatter, one is positive, the other one is positive, the other negative. So atoms, so like this. So atoms, when these two, they will scatter around in the sphere. Positive charge, negative charge. Currency, that this our currency will passes through. So Thomson studied the passage of electric current through a gas. So we saw it in a gas form. We saw it through a gas. So J.J. Thomson first said atoms were smaller than Dalton thought. It then came up with a Coulomb pudding models, which described say atoms were positively charged and negatively charged, which scatter like raisins. Yeah, before you know what the raisins are, they scattered around. Like if you put raisins with the pudding, they scatter. Yeah, this was the J.J. Thomson's experiment in the late 1800s. So the question which arose was in an atom, let's say this was an atom. So the question was, where did the negative charges come from? Yeah. So Thomson concluded that charge, uh, negative charges came from within the atom. So negative charge were within the atom, they were outside, and the atom was also divisible. So Thomson also put the negatively charged for the particles. They, we know them as electrons. Yeah. They call them electrons. That's it. That's the day they are called. So let's look at some which. So Musa for the God for experiment. Don't mind. So Musa Rutherford's God experiments. He was an English scientist, English physicist, Ernest Rutherford. So his experiment was you take a gold ring, and you combat it with particles, and see how those particles will travel around the gold foil. So Rutherford found the so Rutherford took a gold foil experiment, gold foil ring, and fired it with positively charged particles. So this was a source of particles. So, alpha particles. So we fired it in a beam, and then the beam scattered the particles around the both foil. So it found that most of the positively charged bullets pass through the gold atoms without changing cross at all. So the positive ones passed through, like bullets. Bullets pass through objects. So most of the positively charged particles passed through the gold experiment. So we also found out that some positive charged bullets, however, didn't bounce away from the gold sheet as if they hit something solid. He knew, so this is what we say, like against like comes from. So we found out to say in this gold sheet, the positively charged this particles repelled each other. Repelled, they bounce back on each other. So positive, positive as well. So we found out to say in this experiment, the most of the positively charged particles were passing through the the foil, the, the gold foil around the ring, were passing through it. But the one thing, like some did not pass through, it's like they hit something solid. So in this gold foil, there were some positive charges. In this gold foil, there were some positive charges. So if this source of other particles hits a beam of particles. So some particles would pass through like this, pass through, while others bounced back, bounced back after hitting a positive. So this is where positive and positive repel. So positive charges repel each other. So summary of the Rutherford experiment is that first of all, we have found that when you shine a beam of particles in the Godfrey experiment, the positive ones mostly pass through like bullets. So the positive charged bullets they pass through this. While some like they hit something solid, so they didn't go through. Yeah, didn't go through. Okay? So this was the summary. So paper Godfrey experiments. Summary of it. Let's look at the boy mo the boys model. Boys model. So the boys model is an early atomic model. So it was used to this. So in the early 1900s, a scientist by the name of Niels Bohr proposed an improvement to show how electrons orbit in a specific fixed energy level. So the boys model can identify how electrons orbit in a specific energy level or shells. So it shows that in the nucleus, which is here, so the electrons in the nucleus will orbit this energy level. The negative ones in this orbital as well. So this is orbital 1. So these electrons in orbital 2 will be in this same energy level. They won't change energy levels. The Boy's model helps us describe how nucleus. So these electrons in energy level 1 will only orbit in the same energy level. So we have the green ones, we call them electrons. The blue ones are what? Photons. And then these ones are the neutrons. Yeah. Photons, neutrons. Yeah. The electrons are these ones, these energy levels. So in the nucleus, in this nucleus, we have 6 protons and 6. So in what's this? In orbital 1, the maximum number of electrons are 2. In orbital 2, maximum number of electrons are 8. In orbital 3, maximum number are 8. Orbital 4, maximum number of electrons are 18. What for? Here should be 4. Should be 4. So this will be start. If you so here you yeah. So in orbital 1, which is this one, maximum number is 2. In orbital 2, maximum number is 4. Should be 4. Orbital 3, maximum number 8. So on and so on. So each orbital has this maximum number of electrons it can produce. As a maximum number of electrons it can use. So wave model, let's look at it. The wave mode, let's look at the wave mode. So in fact, it is important to determine what exact location an electron is. So the probable location of an electron is based on how much energy the electron has. So we are now trying to see that electrons it is important to determine where they are located. Level 1, 2, 3, 4. It's hard to detect where they are. So what helps us is the energy, the energy it has, energy it has. So in form of according to the model atomic model, an atom has a small positively charged nucleus surrounded by a large region in which there are enough electrons to make an atom. So electron cloud, a space in which electrons are likely to be found. So if you have this is positive, these ones are negative. These negative. These electron are making what? Electron clouds. So basically, electron cloud where there is this positive and it's surrounded by all these negative making electron clouds. So the electron with the lowest level of energy. Since we calculate, we determine where you find an electron based on the energy it has. So the one with the lowest energy. So if we electron has, we give an example, 2 electron has 2 kilojoules, and the other one has 4 kilojoules. So this one with 2 kilojoules of energy will be closer to the nucleus than this one. So if we have to, let's say, electron A, B. So based on the energy, you know electron A will be closer to the nucleus than electron B because the energy at which we are. So the one with the lowest energy, you find it near the nucleus. High energy further from the nucleus. So this helps us determine the location of an electron. So you know the one with the lowest energy further from the nucleus. The one with highest energy further from the nucleus. The one with the lowest energy close to the nucleus. Based on the energy level. know that an electron, one which is into the nucleus, so we know this electron here, it's this is the nucleus. Wow, this one here. So this one has the highest energy. As the highest energy. Wow, this one has the highest energy. This one, low energy. This one has the highest energy. This one has the lowest energy. So, we now know electrokinetic energy is wave. So whereby it calculate its energy, and this energy will tell us the specific location at which it is located. Okay? So from an atom, there's one electron. We now know what the electron can do. Atomic structure. An atom is the smallest subunit of matter that retains the identity of the substance. We've already described what an atom is. We now know, yeah. So an atom has two regions, the nucleus and the electron cloud. Nucleus is the center of the atom, contains most of the mass of the atom. So the mass of the atom is found in the nucleus. And then the electron cloud surrounds the nucleus and takes up most of the space of an atom. So let's see. So so what perfect can it bad? Okay. So we know this right here inside this is small user the nucleus. So this one is our nucleus. So yeah. Then these things right here, I have to put so many of these, if one is here, one there, now they are forming what? Electron cloud, you know. how do they cover up a specific area? So now they're covering up the nucleus. So we have what we call in the nucleus, we find protons which are positively charged particles. And we have what neutrons which are neutrally charged. So each of them have the mass of 1. In the electron cloud, so we found what electrons. So as these ones, right? This one, this one, this one. That's where we found them. They are negatively charged and have a relative mass of this is where relative mass. So in an atom, we have what nucleus and electron cloud. So in the nucleus we find protons and neutrons. In the electron cloud we find electrons. Yeah. So this is the affinity. So how do we know the number of protons in an atom? So atomic number is equal to number of protons in an atom. So when they say atomic number, that's atomic number that just telling you the number of protons in an atom. That's what we mean by atomic number. So carbon atomic is 6. So which means carbon has 6 protons. So and then how do you know the mass number? So the mass number is basically the number of protons plus number of neutrons in the nucleus. That is the mass number. So for example, we have this one. So there is 7 3. The mass of lithium is 7. Atomic is 3. So you're going to do 7 3 for you to get the what? The neutrons. The neutrons will be 4. Okay? So you know protons so this is a mass, this is a atomic number. Subtract this and then you get so isotopes, these are atoms of the same element having different masses. So like carbon, you have carbon 2, carbon 14, carbon 14. Yeah. So these are just isotopes of each other. So carbon 12, which is relatively famous. We have the carbon 14. This carbon 14, which is used to detect what bonds. Bonds. Very good of the carbon 14 machine. Very good of it. The carbon 12 used to liquids, bonds, yeah. So these are just isotopes. Yeah. This carbon 12, we use it for chemical reactions. Then the carbon 13, we use it under mass spec and the NMR. Yeah. So these are just isotopes, carbon. Carbon yes, it's carbon 12, 14, and 14. So each one has specific function. Nature of light. What is light? So light is basically a radiation. Light is it. So the magnetic spectrum includes many different types of radiations. There is the light we see, which is called the visible lights. Then the microwave, the X-ray, all these forms of lights. UV, the ultraviolet lights. So we are going to end here on lights. We continue with this slide. So we end on lights. Continue after some time. Yeah, we can do as a continuation. We believe the light.